Hello everyone, welcome to the channel Statistica Hub. So let's continue our topic system of linear equations. Okay, so now we'll do system of linear equations and linear combination of vectors. Okay, so let's just see this. So we can write our linear equations into this format too, into the vector format like x1, a11, a21 to am1 plus x2, a12, a22 to am2 plus going on xn, a1n, a2n to amn, and that is equals to b1, b2 to bm. Okay, so this is the another way that's how we can write our linear equations too, and this is actually the linear combination of vectors. Linear combination of vectors like v is equals to a1 u1 plus a2 u2 to am um. Okay, so that's how we can write the linear combination is. So I can write the corresponding linear combination here. Let's say this is my vector v1, this is v2, and this is bm. Okay, okay, it will be vn. This is vn, and just consider this is u. Okay, so I can write it as u is equals to v1 x1 plus v2 x2 to vn xn. Okay, so this is what this is actually the linear combination of vectors. Okay, now we have done the concept of dot product. Dot product, in that we have seen this, that if I have this vector u which is a1 a2 to an, okay, and I have another vector v which is b1 b2 to bn, okay, then the corresponding dot product of this u dot v is equals to a1 b1 plus a2 b2 to an bn. Okay, and if we have the dot product u dot v is equals to 0, then we say that u and v are orthogonal. Okay, so by applying the concept of the dot product in this system, we are saying that we have these vectors u1, u2 to un. Okay, let's just I am writing my system of linear equation into the format like v is equals to a1 u1 plus a2 u2 to am. Okay, this is how I'm writing my system of linear equations. Okay, now these vectors u1 u2 to um, which are belonging to r's power n, and these are n non-zero, are n non-zero pairwise orthogonal. What? Pairwise orthogonal vectors. So what is the mean of pairwise orthogonal vectors? That means that ui dot uj is equals to 0 for all I not equals to j. Okay, and ui dot ui is not equals to 0 for each I. Okay, this is the condition for vectors to be pairwise orthogonal. Okay, that ui dot uj, multiplication of the vectors with I not equals to j is equals to, has to be equals to 0, and ui dot ui, multiplication with the dot product with the same vector is not equals to 0. Okay, this is the property of the dot product. So by applying this property, we'll find the linear combination, that is v equals to a1 u1 plus a2 u2 to am um. This linear combination, like how, let's just consider that my v is actually equals to 4 14 minus 9. Okay, this is my v. Okay, and this v is a linear combination of u1 that is 1 1 1, u2 that is 1 minus 3 2, and u3 which is 5 minus 1 minus 4. Okay, now I want to find this linear combination that in that is that v is equals to x u1 plus y u2 plus z u3. Okay, so I want to find this linear combination, and for finding this linear combination we have to find the value of x, y and z. Okay, so if we do this normally, then we have to solve three equations. We can get got there three equations that are like um, by putting the values here like 4 14 minus 9, and x which is 1 1 1 plus y which is 1 minus 3 2 plus z which is 5 minus 5 minus 4. Okay, so after this, if we form the equation, we will have the equation like x plus y plus 5z which is equals to 4, and similarly the second equation and the third equation, and we have to solve these three equations. Okay, and it is very calculative that we have to calculate so much in that case, but we can apply the property of pairwise orthogonal vectors, and by that we can easily find the linear combination here. Okay, so I have to find the value of x y z. So if I take the dot product of this, let's consider this equation 1. If we take the dot product of this equation 1 with respect to u1, that is 1 1 1 with respect to u1, taking the taking dot product with respect to u1. Okay, so we have seen this. If we take the dot product of u1 into u1, we will have the vector as which is not equals to 0. The dot product of u1 with u1 is not equals to 0 by this property, and the dot product of u1 with any other vector which is u1 dot u2, u1 dot u3, that has to be equals to 0 by the property of pairwise orthogonal. Okay, now let's apply this. So if we multiply this u1, we will have let's take another page, which we will have 4 19, it's 19 or it's 14, I think it's 14. Okay, for 4 14 minus 9 and 1 1 1. Okay, and that is equals to x 1 1 1 and 1 1 1. And for the other multiplication we will have 0, because u1 dot u2 is equals to 0 and u1 dot u3 is equals to 0 by the pairwise orthogonal. Okay, so we'll just apply this here. Okay, and we will get if you'll calculate this, this will be 3x and this will be 4 14 and 9. Okay, so x is equals to 3 here. Okay, we don't have to do so much of calculation, and we got our value, first value, which is x is equals to 3. Now in the same equation 1, we'll take the dot product with respect to u2 and u3. Okay, when we take a dot product with respect to u2, we will have 4 14 minus 9, u2 is 1 minus 3 2, and that is equals to y 1 minus 3 2, 1 minus 3 2. Okay, and others will be 0. Okay, so let's just do this, which is 4 plus, okay, minus 4 3 4 8 2 minus 18, and that is equals to this will be 1 9 10 and 2 to the 4 14y. Okay, and that will be equals to 14y, and this will be minus of 8 9 10 minus of 56, that is equals to 14y, and y is equals to minus of 4. Okay, we got our value for of value minus 4 for y, and by taking the dot product with respect to u3, we will get 4 14 minus 9 into 5 minus 1 minus 4, and that is equals to z 5 minus 1 minus 4, 5 minus 1 minus 4. Okay, and that is equals to 40 20. minus 14. Okay, 9 4 42, and this is z, and that will be equals to 25 1 and 4 16 42 42, and that, so we got z is equals to 1. Okay, so the corresponding linear combination of these vectors is v is equals to we have x 3 u1 minus 4 u2 plus u3. Okay, so without doing any without solving any equations, by using the dot product, we have got our linear combination of the vectors, that is v is equals to 3u1 minus 4u2 plus u3. Okay, now let's see homogeneous system of linear equation. Homogeneous linear equations. Okay, so homogeneous linear equations are basically of ax is equals to 0 type. Okay, now let's just consider a which is of n cross n. Now this ax is equals to 0 is homogeneous system. Now this system is necessarily consistent. This system is necessarily consistent because it possesses a trivial solution. It possesses a trivial solution. Trivial solution. By trivial solution we mean that x is equals to 0. Okay, let's say x is equals to 0 is always a solution of this homogeneous system of equation. Okay, because here b is equals to 0, that's why we say that it is always consistent and it possesses a trivial solution, that is x is equals to 0. Okay, so now we have want to know that if there is at least one non-trivial solution. Okay, if there is at least one non-trivial solution, then it's of interest to find the set of maximum number of linearly independent non-null solutions. Okay, so what do we have? A here is A is the coefficient matrix, and if we say that my A is non-singular, okay, if our A is non-singular in this format Ax equals to 0, that means we have rank of A is equals to n. Okay, and in this case when we have A as non-singular, A as non-singular and its rank is n, in this case the only it has only trivial solution. This system has only trivial solution. Okay, or you can say that if rank of A is equals to n, then only trivial solution, then only unique solution, then only unique solution is trivial solution. Okay, okay, so for a solution, for a non-trivial solution, for a non-trivial solution, we should have the rank of this matrix A to be less than n. Okay, then can we have a then can we only have a non-trivial solution. Okay, now there are some note here that if we have x1 and x2, okay, which are the two solutions of this ax is equals to 0. Okay, then the corresponding linear combination of this solution, that is k1 x1 plus k2 x2, this is also a solution of ax is equals to 0. Okay, and the second thing is the number of linearly independent solution of homogeneous system. The number of linearly independent solution of homogeneous system in n unknowns, in n unknowns is n minus r if we have rank of A is equals to r. Okay, the number of linearly independent solution of homogeneous system in n unknowns is n minus r. So how do we get this n minus r? So we get this like by the nullity. Okay, so we have done the concept of nullity, and in that we say that ax is equals to 0 is actually the null space, and this is the homogeneous system in our linear equation system. Okay, and this forms the null space of the matrix A. Okay, and the dimension of this null space of A is basically the n minus r, where n is the unknowns. Okay, n is the number of unknowns. Okay, so the dimension of this null space of A is actually the nullity of A. Okay, nullity of A, and this is my null space of A. So by applying the nullity and null space, we got that the number of linearly independent solutions of homogeneous system in n unknowns is basically n minus r, because it is the nullity, and the solution space of the homogeneous system is actually the null space, and this solution space is forms the vector space. Okay, it forms the solution space. Okay, now let's just see the nature of solution of this nature of solution of this homogeneous system, that is Ax is equals to 0. Okay, so we have this let's say matrix of A m cross n. Okay, and the rank of this matrix A is equals to R. Okay, and by the property of rank, we have this R, which is minimum of m comma n, m comma n. Okay, so we will have either r equals to n or r less than n. Okay, because here we have n unknowns, that is, we can have the rank equals to number of unknowns, and we can have the rank less than unknowns. Okay, so let's just consider the first case when we have r is equals to n, that is, my rank is equals to the number of unknowns. Okay, then in that case we have n minus r, what, n minus r linearly independent solutions of m homogeneous equations. Okay, done that just now. Okay, so if my r is equals to n, then we will have n minus n, that is equals to 0. That means we have 0 linearly independent solutions. Okay, in this case we have 0 linearly independent solution, and in this case we will have a equation only have, in this case the equation only have a trivial solution, trivial solution. Okay, and the second thing is, if r is less than n, in this case we say that it possesses a non-trivial solution. Okay, it will, the system will only possess a non-trivial solution when our rank is less than number of unknowns, or number of its columns, number of unknowns. Okay, now the, if we talk about the number of linearly independent solutions, then n minus r, n minus r are the number of linearly independent solutions here, and they are actually the infinitely infinite many solutions. In this case we will have infinite many solutions. Okay, so this is the nature of the solution of the homogeneous linear equation. If we have a unique solution in the homogeneous system, that has to be trivial only, because that's the case only when we have the rank is equals to the number of columns, or you can say number of the unknowns. Okay, now the homogeneous linear system actually possess a very important property of the solution space. Its solution space, let's just talk about that. Okay, talking about the solution space of this homogeneous system, then the vector space is sorry, vector space generated by solution of Ax is equals to 0 is actually the solution space. Okay, now what is our solution space is that we have Ax is equals to 0. This is the homogeneous system that we have. Okay, all the values of x, for that Ax is equals to 0, and this is actually the null space of A. Okay, we have done this in the nullity and null space concept. Okay, this is the null space of A, and what is the dimension of this null space of A? The dimension of this null space of A is equals to n minus r. Okay, and if this n minus r is 0, then we have a trivial solution, and if this is greater than 0, then we will have a non-trivial solution, non-trivial solution. Okay, so let's just consider that if the dimension, that is, if the nullity of A, if the nullity of A is greater than 0. Okay, so in this case we may search for basis of solution space. Okay, we can search for basis of solution space. So suppose that x1, x2 to x n minus r, these be the bases of the solution space. Okay, let this is the basis of solution space. Okay, now as these are the bases of the solution space, then any solution of this ax is equals to 0 can be written in the linear combination of these basis vectors. Okay, by the property of basis. That is, from this we say that the general solution to the system of equation will be of form something like sigma I equals to 1 to n minus r lambda I xi. Okay, so the general solution of the system of equation will be of form like this, because we are considering if we have the nullity greater than 0, that means if we have a non-trivial solution, then we have a basis of the solution space, and these bases we have considered these basis vectors here. Okay, and we have said that as these are the basis vectors, then every vector in this system can be written in the linear combinations of these basis vectors. Okay, so by using that property, we will have a general solution of this system, something like this. Okay, now this form that the nullity of A, or you can say the number of linearly independent solutions in uh, linear homogeneous equation, is of great use. Like we have this, let's say, matrix of 20 cross 50. Okay, I have this matrix and I have this dimension of row space of A, that is equals to 13. Okay, now I want to find that what is the dimension of solution space of A. Solution space of A, sorry, solution space of Ax equals to 0. We have to specify that this is the homogeneous system. What is the dimension of solution space of Ax equals to 0? So we have just done that the dimension of the solution space of Ax equals to 0 is n minus r, that is the nullity of A. Okay, so talking about that, let's just see that W is our solution space. W is our solution space. That means our x, all the x's belongs to r's power 50. That is columns. Okay, that is the number of unknowns. Okay, x belongs to 50 for all ax equals to 0. Okay, now the dimension of this W will be equals to n minus r. And what did we have n? N is my 50. Okay, and r is minus 13. Minus 13, because dimension of row space of A is basically the rank. Okay, 50 minus 30, we will have 37. So the dimension of the solution space of Ax equals to 0 is equals to 37. Okay, okay. Now let's do an example, which is that we have this system which of equations like x1 plus 2x2 minus x3, which is equals to 10, minus of x1 plus x2 plus 2x3, that is equals to 2, and 2x1 plus x2 minus 3x3 is equals to 8. Okay, so we have these three linear equations here. Let's write them into the augmented form, which is 1 minus 1 2, 2 1 1, minus 1 2, minus 3, and 10 2 8. Okay, now reduce them into the canonical form. Let's apply the transformation, like in R2 we will apply R2 plus R1, and in R3 we will apply R3 minus 2R1, and that will be equals to 1 2 minus 1 10, 0 3 1 12, and this is 0 minus 3 minus 1 and minus 12. Okay, okay, so let's apply the transformation in R3, which is R3 plus R2, and we will get 1 2 minus 1 10, 0 3 1 12, 0 0 0 0. Okay, now let's reduce this to the canonical form. For reducing this to the canonical form, we will divide R2 by 2. Oh, sorry, by 3. Okay, so if we divide R2 by 3, we will have this as 1, this as 1 by 3, and this will be 4. Okay, now for this reduce this matrix, we have to make this 0 to, okay, so we'll do R1, you'll apply in R1 minus 2R2. Okay, and that will be equals to 1, 0, and this is minus of 5 by 3, and this is 2. Okay, 0 0 1 0 1 by 3 0 4 0. Okay, so we have reduced this to the canonical form because pivot element is the only element which is non-zero and in the column. Okay, so we have reduced this into the echelon form. Now let's just form the equations here. So after, if we form the equation, that will be like x1 minus 5 by 3 x2 is equals x3. Okay, it's 5 by 3, that is 5 by 3, x3 is equals to 2, and the second equation will be x2 plus x3 by 3 is equals to 4. Okay, so we have x1 and x2 into our pivot column. Okay, so x1 and x2 are basically pivot element. Okay, and we will have x3 as it doesn't have any pivot, so it is my free variable. Okay, so let's just consider that x3 is equals to c. Okay, and find the other uh, unknowns, that is x1 will be equals to 2 plus 5 by 3 c, and x2 will be equals to 4 minus c by 3. Okay, so our solution will be like 5 by 3 c plus 2 comma 4 minus c by 3 comma c. Okay, and we can also write this as c by taking out c in common. We will have 5 by 3 comma minus 1 by 3 comma 1 plus 2 4 0. Okay, so look at this solution here. This is said to be my particular solution of system. This is particular solution of system, and this is actually the general solution system of system. This is the general solution of system. Okay, if we talk about the basic, that it then it will contain actually infinite number of solution. This system contain infinite number of solution because it has the rank of augmented equals to rank of a. Okay, but this is not equals to the number of unknowns. Okay, so we will have here infinite number of solutions because we can give any value to the c. Okay, so this is the general solution of the system, and this is basically the particular solution of the system. Okay, now let's talk about consistency criteria. Okay, so the consistency criteria in the homogeneous system is like, if we have determinant of a is not equals to 0. Okay, that means we have the invertible matrix. If we have a which is invertible matrix, then the system is consistent and has unique solution and has unique solution. Okay, and the unique solution is basically the x is equals to a inverse b. X is equals to a inverse b. Okay, so this is how we can check a consistency criteria. Sorry, I had, did I say homogeneous? No, it's basically for ax is equals to b, not for the homogeneous only. It's a for ax equals to b. Okay, so if we have determinant of a is equals to 0, okay, that means if the matrix is not invertible, in this case, adjoint of a into b is equals to 0. Okay, if we have the format like this, that the adjoint of a into b is equals to 0, then this is consistent and has infinite number of solutions. Okay, And if we have adjoint of A into B, which is not equals to 0, okay, then in this case, it is inconsistent system. Inconsistent and hence has no solution. Okay, so this is the criteria. That's how we can check whether a system, that is ax equals to b, is consistent or not. Okay, so if the matrix A is invertible, that means determinant of A is not equals to 0, then it is consistent and has a unique solution, and we can find the unique solution by x is equals to A inverse B. Okay, and if we have determinant of A that is equals to 0, um, that means the matrix A is not invertible, then we have to check that whether the adjoint of A into B is equals to 0. Okay, if it is so, then the system is consistent and has infinite number of solution. Okay, and if the adjoint of A into B is not equals to 0, then the system is inconsistent and hence has no solution. Okay, so this is the criteria. That's how we can check the consistency of any system of linear equation. Okay, so that's all for now. In the next lecture we will do a homogeneous system of linear equation and uh, take a basic knowledge of the generalized inverses of the matrices. Okay, thank you.